Hello there, and welcome to Beyond the Cosmos, where the biggest questions in science are explored at the pace of a slow breath, where curiosity is never rushed, and where the universe unfolds one careful thought at a time. Tonight, we are going to sit with something that is, in the most literal sense possible, happening to you right now. Not something that happened long ago in the distant past of the cosmos. Not something that will happen billions of years from now. Something that is happening at this very moment, as you lie here, as your eyes grow heavy, as the sounds of the world outside soften and fade. The Milky Way is falling. Not falling the way a stone falls from a table, not falling the way rain falls from a cloud, but falling in the way that the universe understands falling, which is to say, being pulled, being drawn, being called slowly and irresistibly across millions of light years of space towards something so massive and so strange that it took astronomers decades to even agree that it existed. Something hidden behind a curtain of dust and stars so thick that visible light cannot pass through it. Something that has been pulling at our galaxy since long before a single human being looked up at the night sky and wondered what was there. That something has a name. It is called the Great Attractor. Before we set off into this together, I want to ask where you are tonight. Perhaps you are in bed, the room dark, the covers pulled close. Perhaps you are on a sofa with the lights dimmed, the day finally letting go of you. Maybe you are somewhere with a window, and if you looked out right now, you would see a sky with a few stars, or perhaps many, depending on where in the world you find yourself. Wherever you are, the ground beneath you, the building around you, the planet under your feet, all of it is moving. All of it is falling, gently and continuously, in the direction of something vast and invisible. And tonight, we are going to find out what that something is. If this kind of slow, careful exploration of the universe brings you comfort or helps you find rest, please consider tapping the like button or subscribing to Beyond the Cosmos. It helps more people find their way here, to this quiet space where science moves at the pace of a thought rather than the pace of a headline. Now, take a breath, let your body settle, and let's begin. There is a particular kind of wonder that comes from learning that something you thought was still is actually moving. A child discovers that the ground beneath their feet is not fixed, but is part of a planet spinning at over 1,000 kilometers per hour. A student learns that the solar system is not sitting quietly in space, but is orbiting the center of the Milky Way at roughly 230 kilometers per second. An astronomer discovers that the Milky Way itself, all of its hundreds of billions of stars, all of its dark matter and gas and dust, is moving through space at hundreds of kilometers per second towards something we can barely see. Each of these revelations has the same quality: a sudden shift in the sense of the ground beneath your feet, a realization that what felt like stillness was never stillness at all, only motion, too large and too slow to notice in the ordinary course of a human life. The motion of the Milky Way toward the Great Attractor is one of the largest of these revelations. It is not a small or local movement. It is not the orbit of the Milky Way around some nearby concentration of mass. It is a large-scale flow, a drift of our entire galaxy, along with thousands of other galaxies across hundreds of millions of light-years of space toward a region so densely packed with matter that its gravitational influence extends across a significant fraction of the observable universe. To understand why this matters and why it is so strange, it helps to begin with what we thought we knew about the motion of galaxies before the Great Attractor was discovered. For most of the 20th century, the dominant picture of cosmic motion was relatively simple. The universe is expanding. Galaxies are moving apart from one another. The farther away a galaxy is, the faster it appears to recede. This relationship, discovered by Edwin Hubble in the 1920s, is called the Hubble flow, and it is one of the most fundamental facts of modern cosmology. But here is the thing about the Hubble flow. It is an average. It describes the overall expansion of space, the general tendency of galaxies to move apart. What it does not capture is the local, peculiar motions of individual galaxies, the deviations from the smooth expansion caused by the gravitational pull of nearby concentrations of mass. These These peculiar velocities are superimposed on the Hubble flow, adding and subtracting from it depending on the direction and magnitude of the gravitational forces at play. In the 1970s and 1980s, astronomers began to notice something troubling when they looked carefully at the peculiar velocities of galaxies in our cosmic neighborhood. The galaxies were not moving purely in accordance with the Hubble flow. They were, on average, streaming in a particular direction, not randomly, not chaotically, but together in a coordinated flow, as though something vast and massive lay in that direction and was pulling them toward it. The Milky Way was part of this flow. We were falling, along with thousands of our galactic neighbors, towards something we could not directly see. That was the first hint of the Great Attractor, and it raised an immediate question that would take decades to partially answer. What was pulling us, and what was hiding it from view? To appreciate why the Great Attractor was so hard to find, you need to understand where it is and what lies between us and it. The Great Attractor is located in the direction of the constellation Norma in the southern sky. Norma is not one of the famous, easily recognized constellations. It is a small, faint grouping of stars in the plane of the Milky Way, not far from Scorpius. And that location, in the plane of the Milky Way, is the heart of the problem. The plane of the Milky Way is where most of the galaxy's stars, gas, and dust are concentrated. It is the bright band you see stretching across the sky on a dark night, the edge-on view of our galaxy's disk. Looking in any direction along that plane means looking through an enormous thickness of interstellar material, dust clouds that absorb and scatter visible light, stellar populations so dense that individual objects behind them are hidden. This region of the sky is sometimes called the zone of avoidance, not because astronomers choose to avoid it out of preference, but because the density of intervening material makes it nearly impossible to see through invisible light. The Great Attractor lies almost exactly behind the zone of avoidance. If you wanted to design a hiding place for something massive and cosmologically important, you could not do much better. It sits behind the thickest, most obscuring part of our own galaxy, effectively veiled from optical telescopes by billions of solar masses of dust and gas. This is why the Great Attractor was not seen before it was felt. Astronomers noticed the motion of galaxies toward it, the gravitational signal of its mass, before they had any clear idea of what was actually there. It was inferred from its effects, like a planet whose presence is revealed by the wobble it induces in the star it orbits, before anyone photographs the planet directly. The Great Attractor was, for a significant period of its history, a gravitational ghost, a force without a clearly visible source. Over time, as radio telescopes and infrared and X-ray observatories came online, as technologies that could see through the dust of the zone of avoidance became available, the picture slowly cleared. What emerged was something more complicated and more magnificent than a single hidden object. The Great Attractor is not a point. It is not even a single cluster of galaxies. It is an extended region of space, a concentration of mass that spans tens of millions of light years, and at its heart lies one of the most spectacular concentrations of galaxies known in the observable universe. But let's not move too quickly. Let's stay a little longer with the question of what it means for a galaxy to fall. When we say the Milky Way is falling toward the Great Attractor, we are using the word falling in a precise scientific sense that is worth unpacking carefully. In everyday life, falling means moving downward under the influence of gravity. A dropped coin falls toward the floor. A raindrop falls toward the ground. The direction of the fall is determined by where the gravitational source is, which in everyday experience is always below you, toward the center of the Earth. Falling is associated with a clear directionality, a clear destination, and usually with increasing speed. In the context of the Milky Way and the Great Attractor, all of these elements are present, but at a scale that makes them unrecognizable in ordinary terms. There is gravity. There is a source of that gravity, the concentrated mass of the Great Attractor region. There is a direction toward that source, and there is a kind of acceleration, though so gentle and so slow compared to human timescales that it is entirely imperceptible. The difference is that this fall is happening through space rather than through air. There is no atmosphere to rush past, no sensation of wind, no feeling of weight or weightlessness. The Milky Way is moving through the vacuum of intergalactic space, and nothing about that motion can be felt by anyone inside the galaxy, any more than you can feel the Earth moving around the Sun or the solar system moving around the galactic center. The motion is real, it is measurable, it is consequential on the scale of cosmic history, but it is utterly invisible to ordinary experience. The speed of this fall is also worth contemplating. Our galaxy is moving toward the Great Attractor region at roughly 600 kilometers per second, as part of a larger flow that encompasses not just the Milky Way, but our entire local group of galaxies and many other groups beyond it. 600 kilometers per second. That is more than 2 million kilometers per hour. In a single day, the Milky Way moves roughly 50 billion kilometers in the direction of the Great Attractor. And yet, because the distance to the Great Attractor is so enormous, hundreds of millions of light years, this motion is barely a whisper against the scale of the journey. Even at 600 kilometers per second, reaching the Great Attractor would take billions of years. The fall is real and fast by human standards, and at the same time slow and incomplete by cosmic ones. There is something grounding about this. The universe operates on timescales that dwarf human experience so thoroughly that even the most dramatic motions, a galaxy hurtling through space at hundreds of kilometers per second, amount to almost nothing in the time it takes for a civilization to rise and fall. We are passengers on a vessel that is moving faster than we can imagine, toward a destination we may never reach, and we feel none of it. The story of how the Great Attractor was discovered is a story about the careful, painstaking measurement of extremely small deviations from an expected pattern. It is a story about the kind of science that requires not dramatic observations or sudden revelations, but the accumulation of precise data from hundreds of galaxies and the statistical tools to find a signal buried in noise. In the 1970s, astronomers developed methods for measuring the distances to galaxies using what are called standard candles and standard rulers. Certain types of stars, certain properties of galaxies, have known intrinsic brightnesses or known intrinsic sizes. By measuring how bright or how large they appear in the sky, you can calculate how far away they are. With distances in hand and with redshifts measured from spectra, you can calculate how fast a galaxy is moving away from us, and then compare that to how fast it should be moving if it were following the Hubble flow perfectly. The difference between how fast a galaxy is actually moving and how fast the Hubble flow predicts it should be moving is the peculiar velocity. A galaxy with a positive peculiar velocity relative to the Hubble flow is moving away from us faster than expected. A galaxy with a negative peculiar velocity is moving toward us, or more slowly away from us than expected. These peculiar velocities are small compared to the Hubble recession velocities of distant galaxies, but they are measurable with care. In the late 1970s and through the 1980s, several groups of astronomers began comparing peculiar velocities of galaxies in our local region of the universe. They found something remarkable. The peculiar velocities were not random. They were systematically pointing in the same direction. Galaxies in our cosmic neighborhood, including galaxies that were supposed to be moving away from us with the Hubble flow, were instead streaming toward a point in the sky in the direction of the constellation Norma and the southern Milky Way. The magnitude of this streaming was also remarkable. The velocities implied a source of gravitational attraction with a mass of tens of thousands of times the mass of the Milky Way. Not a cluster of galaxies, not a supercluster. Something larger, something more massive, something that had no obvious visible counterpart in the catalogues of the time. A group of astronomers, who would come to be known informally as the Seven Samurai, published a landmark paper in 1988 in which they systematically measured the peculiar velocities of a large sample of elliptical galaxies and concluded that there was a massive concentration of matter in the direction of Hydra and Centaurus, which they called the Great Attractor. The name was vivid and the result was controversial. Some astronomers doubted the measurements, others questioned the interpretation. The debate would continue for years, but the core finding held up. Something massive was there, in that direction, exerting a gravitational pull on everything nearby. The Milky Way was falling toward it, and the challenge now was to figure out what it was. The Seven Samurai gave the Great Attractor its name, but understanding what it actually is took another 2 decades of increasingly sophisticated observations. The story of that understanding is a story about what lies hidden behind the zone of avoidance and what telescopes operating at wavelengths other than visible light can reveal. Radio waves, infrared radiation, and X-rays pass through the dust of the Milky Way's plane far more easily than visible light. A cloud of dust that completely blocks a background galaxy in an optical telescope may be nearly transparent to a radio antenna or an X-ray detector. This opened up the zone of avoidance to a new generation of surveys. In the late 1980s and 1990s, surveys conducted in the infrared and radio began to reveal the galaxy population hiding behind the obscuring layer of our own Milky Way. What they found in the direction of the Great Attractor was extraordinary. There was not one galaxy cluster there. There were many, a concentration of clusters and superclusters of galaxies forming one of the richest and most massive regions of the observable universe. At the heart of this concentration lies the Norma Cluster, also known by its catalog designation Hubble 3627. The Norma Cluster is one of the most massive galaxy clusters known, containing thousands of galaxies bound together by gravity in a dense concentration. It sits almost exactly in the zone of avoidance, which is why it was not identified as a major cluster until relatively recently. Even today, studying it requires infrared and radio observations rather than optical ones. But the Norma Cluster, massive as it is not the whole story. Surrounding it is an extended region of enhanced galaxy density, filaments and walls, and groups that together constitute what is now understood as the Centaurus Supercluster, which is itself part of an even larger structure. The Great Attractor is not a single object, it is a region, an overdense patch of the cosmic web that covers tens of millions of light years and contains a mass that is genuinely difficult to express in comprehensible terms. Estimates of the total mass required to explain the observed peculiar velocities of galaxies in the surrounding region run into the range of several 100,000 times the mass of the Milky Way, concentrated in a region perhaps 250 million light-years across. That is a number so large that it becomes almost meaningless as a direct comparison. But it is real. It is there, and its gravity has been pulling at our galaxy since long before the Earth existed. There is a detail about the Great Attractor story that is easy to overlook, but that becomes more extraordinary the longer you sit with it. The fact that our galaxy is falling toward the Great Attractor was discovered not by observing the Great Attractor directly, but by measuring how it affects the motion of everything around it. We found it by feeling its pull before we could see it. This is not so different from the way many important things in the history of science have been found. Neptune was predicted before it was observed, its existence inferred from the gravitational perturbations it caused in the orbit of Uranus. Dark matter was proposed as an explanation for the rotation curves of galaxies before any candidate particle for dark matter was identified. The Higgs boson was predicted by theory decades before the particle accelerators powerful enough to detect it were built. In each case, something invisible or hidden made its presence known through its effects on things that could be seen. Gravity is particularly good at this. Gravity cannot be shielded. It cannot be blocked by dust or gas or any other intervening material. A massive concentration of matter will exert its gravitational influence on everything around it, regardless of whether anything blocks the view between the observer and the concentration. The Great Attractor, hidden behind the zone of avoidance, could not be seen. But it could be felt in the systematic streaming of hundreds of galaxies toward its location. This is one of the most beautiful aspects of gravitational science. Gravity is a communicator. It tells you something is there even when you cannot see it. The motion of the Milky Way toward the Great Attractor is, in this sense, a message, a signal written not in light but in velocity, and astronomers learned to read it. Reading that message required extraordinary precision. The peculiar velocities involved are small fractions of the Hubble recession velocities of the galaxies. A galaxy at 100 million light-years is receding at roughly 7,000 kilometers per second due to the Hubble flow. Its peculiar velocity due to the Great Attractor might be a few hundred kilometers per second, a few % of the total. Extracting that signal from the noise required careful measurements of galaxy distances, careful calibration of the distance indicators used, and careful statistical analysis to average over the scatter in the data. The scientists who did this work were doing something quietly heroic. They were measuring the universe's largest gravitational structures by looking at how galaxies deviate by tiny fractions from the smooth expansion of space. The Great Attractor was hidden twice, once behind the dust of the zone of avoidance and once behind the noise and uncertainty of the measurements. Finding it required both better observations and better analysis. Once the Great Attractor was identified as a real feature of the universe and its approximate location and mass were established, a new question immediately arose. Is the Great Attractor the end of the story? Is it the ultimate destination of the Milky Way's motion? Or is the Great Attractor itself falling toward something else? This question turned out to have a profound answer, and the answer changed the way astronomers think about the large-scale structure of the universe and our place within it. The Great Attractor, it turns out, is not itself the final destination. It is a waypoint, a massive concentration of matter that is itself being pulled, along with everything falling toward it, towards something even larger and more distant. That something is called the Shapley Supercluster. The Shapley Supercluster is named for Harlow Shapley, the American astronomer who first noted an unusual concentration of galaxies in that region of the sky in the 1930s, long before anyone understood its significance. It is located roughly 650 million light-years from the Milky Way in the direction of the constellation Centaurus. It is one of the most massive concentrations of matter in the observable universe, a dense aggregation of galaxy clusters and superclusters containing a total mass estimated at tens of millions of times the mass of the Milky Way. The Shapley Supercluster is pulling at everything in a large volume of the universe, including the Great Attractor region, including our local supercluster, including the Milky Way. The flow that carries the Milky Way toward the Great Attractor is part of a larger flow that carries both the Milky Way and the Great Attractor toward Shapley. This is a picture of nested gravitational influences, each one embedded in and drawn by a larger one. The Milky Way is pulled by the local group. The local group is pulled by the Virgo cluster. The Virgo cluster and the local supercluster are pulled by the Great Attractor region. The Great Attractor region is pulled by the Shapley Supercluster. and all of this is embedded in the even larger structure of the cosmic web. The motion of our galaxy is not a simple fall toward a single point. It is a complex resultant of many gravitational influences operating at different scales, from the relatively modest pull of nearby galaxy groups to the enormous pull of the Shapley Supercluster hundreds of millions of light-years away. Untangling these influences, identifying which structures are contributing how much to the observed flow, has been one of the central challenges of large-scale structure cosmology for the past several decades. In 2014, a landmark paper by Brent Tully and his collaborators introduced a new concept that helped clarify the picture considerably. They mapped what they called the Laniakea Supercluster, and in doing so, gave our cosmic home a new and larger address. The word Laniakea comes from the Hawaiian language and means something like immeasurable heaven or immeasurable sky. It was chosen to reflect the scale of the structure being named, something so vast that the ordinary measures of the universe strain to contain it. Tully's team approached the problem of mapping large-scale structure in a new way. Rather than simply cataloging where galaxies are, they mapped how galaxies are moving. By measuring the peculiar velocities of thousands of galaxies and tracing the flow lines of those velocities, they could identify the watershed boundaries of gravitational influence. Just as a continental divide separates river systems that flow toward different oceans, the boundaries of Laniakea separate regions of space whose galaxies flow toward different attractors. What they found was that the Milky Way, the Local Group, the Virgo Cluster, the Great Attractor region, and thousands of other galaxies are all part of a single gravitational basin. All of them are flowing toward the same general region of space, the dense core of what Tully's team called the Laniakea Supercluster. All of them share a common gravitational fate, at least on the timescales over which dark energy has not yet overwhelmed the local gravitational pull. Laniakea is enormous. It spans roughly 520 million light-years in its longest dimension and contains a total mass of around 100 million billion solar masses. The number is staggering, but more important than the number is the concept. For the first time, astronomers had a way of defining the boundaries of our cosmic supercluster not by the positions of galaxies, but by the flows of galaxies, by which way everything is moving. The Great Attractor in this picture is not a single object, but the gravitational focal point of the Laniakea Supercluster, the center toward which the flow lines converge. It is the cosmic equivalent of the lowest point in a vast gravitational basin, the place toward which everything in the basin is, in some sense, falling. And the Milky Way, on its edge, far from the center, is one of the galaxies in that basin. Falling slowly, along with all its neighbors, toward the center of a supercluster it did not even know it belonged to until a team of astronomers mapped the flow of the universe in 2014. Let's pause here and try to picture what this means in physical terms, because the concepts involved can become abstract quickly, and it is worth anchoring them in something more concrete. Imagine a very large, shallow bowl. Not a perfect bowl, but an irregular, lumpy one, with bumps and ridges on its interior surface. Now imagine that this bowl is filled with a thin layer of sand, and that the sand is slowly sliding toward the lowest points in the bowl. Not quickly, not in a rush, but steadily, always moving a little bit toward whatever is lower, diverted and channeled by the bumps and ridges, but always, on average, heading downward. The bowl is a rough analogy for the gravitational landscape of the Laniakea Supercluster. The lowest points in the bowl correspond to the densest concentrations of mass: the Great Attractor region, the Norma Cluster, the extended concentration of galaxies in that part of the sky. The bumps and ridges correspond to the less massive but still significant concentrations of mass in the supercluster, the Virgo cluster, the various galaxy groups and filaments that populate the region. And the sand is everything else, all the galaxies including our own. Each grain of sand a galaxy sliding slowly toward the lowest point it can find. The Milky Way is one grain of sand in this bowl, located somewhere near the rim, far from the deepest point, sliding inward at a rate that is fast by human standards and slow by cosmic ones. The other grains of sand around it, the other members of the local group, the nearby groups and clusters, are sliding in the same general direction. Together, they form a stream, a flow, a coordinated drift toward the heart of the supercluster. The bumps and ridges in the bowl, the local concentrations of mass, mean that the path is not a straight line. The Milky Way is not falling directly toward the Great Attractor in a simple radial trajectory. Its path is shaped by all the gravitational influences it encounters along the way, the pull of the Virgo cluster in one direction, the pull of smaller nearby groups in another, the overall trend toward the supercluster center cutting through all of them. This is why measuring the peculiar velocities of galaxies and tracing the flow lines is so important. The flow lines are the paths that the grains of sand take as they slide toward the lowest points. Mapping the flow lines maps the gravitational landscape. Knowing the gravitational landscape tells you where the mass is concentrated, even when that mass is hidden behind dust or embedded in structures too diffuse to identify by looking for clusters of galaxies alone. One of the questions that arises naturally when thinking about the Milky Way falling toward the Great Attractor is whether it will ever arrive. Will our galaxy eventually reach the center of Laniakea? Will it fall into the Norma Cluster or the dense heart of the Great Attractor region? The answer is almost certainly no, and the reason is one of the most important facts about the universe that was discovered in the late 20th century. The universe's expansion is accelerating. In 1998, two independent teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, announced results from observations of distant Type 1a supernova that upended expectations. The expansion of the universe, rather than slowing down under the gravitational pull of all the matter within it, was speeding up. Space was stretching faster and faster, and the agent of this acceleration, whatever it is, was given the name dark energy. Dark energy changes everything about the long-term fate of the Milky Way's fall toward the Great Attractor. In a universe without dark energy, the fall would eventually carry the Milky Way toward the Great Attractor center, though on timescales of billions of years. The gravitational pull of the concentrated mass would ultimately overcome the Hubble flow and draw nearby galaxies together. But in a universe with dark energy, the accelerating expansion eventually overwhelms all but the strongest gravitational bonds. The scale at which gravitational attraction can win against dark energy is limited. Within the local group, and within the most massive clusters of galaxies, gravity is strong enough to hold things together. The Milky Way and Andromeda will merge in a few billion years. The galaxies of the Virgo cluster will remain gravitationally bound. But on the scale of the Laniakea Supercluster, which spans 520 million light-years, the accelerating expansion is eventually expected to pull things apart. The flow toward the Great Attractor is real. The Milky Way is genuinely moving toward it, but on the timescales over which dark energy becomes dominant, the flow will slow, stop, and eventually reverse. Galaxies that are currently falling toward the Great Attractor will eventually be carried away from it by the expansion of space, their peculiar velocities overcome by the relentless push of dark energy. So the answer to whether the Milky Way will reach the Great Attractor is probably not. We are falling toward it now. We will continue to fall toward it for a very long time. but we will likely never arrive, because the universe's expansion will eventually slow and then reverse our progress, carrying us away from the destination we were heading toward. There is something poignant about that. To fall toward something for billions of years and never quite reach it. To be perpetually en route, perpetually approaching, but always separated by the stretching of space from the thing you are drawn toward. It is a kind of cosmic asymptote, always getting closer in one sense, always receding in another. The Laniakea Supercluster and the Great Attractor at its heart are remarkable structures, but they are themselves embedded in an even larger context. To understand the full picture of what the Milky Way is falling into, and what that falling tells us about the universe, we need to step back further and think about the cosmic web. The cosmic web, as we have explored in previous episodes, is the large-scale structure of the universe. Filaments of galaxies stretching across hundreds of millions of light years. Walls where filaments intersect. Clusters and superclusters at the nodes where walls and filaments meet. And voids, the enormous empty regions that occupy most of the volume of the universe. Laniakea is one node in this web. It is a particularly massive and extended node, one of the largest structures we can identify, but it is connected to and embedded in the larger web. The flow of galaxies toward the Great Attractor is one current in a larger system of flows that traces the shape of the cosmic web. Galaxies flow out of voids, along filaments toward walls, and from walls toward the massive nodes at the web's intersections. The Milky Way's fall toward the Great Attractor is, in the deepest sense, a participation in the large-scale structure formation process of the universe. Near Laniakea, other superclusters exist. The Perseus-Pisces Supercluster lies on the other side of the sky from Laniakea, another massive concentration pulling at galaxies in its own basin. The Shapley Supercluster, which we mentioned earlier, sits beyond Laniakea and exerts its gravitational influence on everything in a vast volume. Coma, another massive cluster, lies in a different direction. All of these structures are connected by filaments. The space between them is not uniformly empty, but threaded with the thin bridges of the cosmic web, flows of matter connecting the massive nodes. The Milky Way's trajectory through space is shaped by all of these influences, though the dominant pull, the one that defines the overall direction of motion, comes from the dense region of the Great Attractor and, at larger scales, from the Shapley Supercluster. Mapping these flows and understanding how the different massive structures in our cosmic neighborhood contribute to the overall motion of the Milky Way has been a major project of observational cosmology over the past 3 decades. It requires surveys of hundreds of thousands of galaxies, measurements of their distances and velocities, and sophisticated computational methods to separate the different gravitational contributions. The picture that has emerged is one of extraordinary complexity and coherence, a web of flows and counterflows that together describe the motion of everything in the observable universe. There is another dimension to the story of the Milky Way's fall that is worth sitting with for a moment, because it connects the very large to the very intimate. The motion of the Milky Way toward the Great Attractor is not just a fact about our galaxy. It is a fact about us, about every human being who has ever lived and everyone who ever will, about every organism that has ever existed on this planet, about the planet itself and the solar system and everything in it. We are all passengers on the Milky Way. We are all falling together toward the Great Attractor at 600 kilometers per second, whether we know it or not, whether we can feel it or not. This motion has been happening since the Milky Way formed, billions of years ago. It was happening when the first single-celled organisms appeared in the oceans. It was happening when the first fish crawled onto land. It was happening when the first humans looked up at the night sky and saw, for the first time, the patterns of stars that they would name and tell stories about. And the motion will continue. It will continue through whatever future the Milky Way has, through the eventual collision with Andromeda, through the long, slow evolution of the merged galaxy that will result, through whatever comes after that in the unimaginably distant future of the cosmos. The fall toward the Great Attractor is one of the constants of our cosmic existence, as fundamental to our situation as the orbit of the Earth around the Sun or the rotation of the Milky Way around its own center. To know this is to carry a strange and beautiful piece of information. You are, at this moment, hurtling through space at hundreds of kilometers per second in the direction of a massive concentration of matter that lies hundreds of millions of light years away. You cannot feel it. You cannot see it. You cannot do anything about it. But it is happening, and it has been happening for as long as anything on this planet has existed. There is a kind of comfort in that, strange as it may seem. The fall is not new. It is not a threat. It is simply the universe doing what it does, matter responding to the gravity of other matter, structure forming on the grandest scales. You are part of that structure. You are one small piece of one small planet orbiting one ordinary star in one ordinary galaxy that is participating, along with thousands of its neighbors, in the largest gravitational dance that the observable universe has produced. Let's turn now to the question of how we know what we know about the Milky Way's motion, because the methods involved are both ingenious and humbling. Measuring the motion of our own galaxy is, in some ways, harder than measuring the motion of other galaxies. We are inside the Milky Way. We cannot step outside and observe our galaxy's velocity from an external vantage point. We have to infer our motion from indirect evidence, from the effect that our motion has on observations we make of things outside our galaxy. The primary method is the measurement of galaxy redshifts and distances. If we know how fast a galaxy should be receding from us due to the Hubble expansion, and we measure how fast it is actually receding, the difference is the peculiar velocity. If galaxies in a particular direction are systematically receding more slowly than expected or are even approaching us, it suggests that both we and they are being pulled in the direction of something massive. By mapping these systematic deviations across large numbers of galaxies in many directions, astronomers can infer both the direction and the magnitude of the overall peculiar flow. But measuring galaxy distances with the precision needed to detect peculiar velocities is extremely challenging. The distance indicators used, the Tully-Fisher relation for spiral galaxies and the fundamental plane for elliptical galaxies, have scatter. Individual galaxies may deviate from the expected relation for intrinsic reasons unrelated to their distance. This scatter is noise in the peculiar velocity signal, and separating real flows from this noise requires large samples and careful statistical methods. The technology and methodology have improved dramatically over the decades since the Seven Samurai first identified the Great Attractor flow. Surveys like the Cosmic Flows program, led by Brent Tully, have measured distances and peculiar velocities for tens of thousands of galaxies, producing maps of the velocity field of the local universe with unprecedented detail. These maps are what allowed Tully's team to define the boundaries of Laniakea and identify the Great Attractor as its central focal point. The measurements reveal something beautiful when you look at them in the right way. Not just a list of velocities, but a coherent picture of motion. Galaxies flowing out of voids, galaxies streaming along filaments, galaxies converging on the dense nodes of the cosmic web, and our own galaxy, among thousands of others, drifting steadily toward the concentration of mass that gives Laniakea its gravitational identity. It is a picture that could only be assembled piece by piece, galaxy by galaxy, measurement by measurement, over decades of careful observation. and the result is a map not of where things are, but of where things are going. A snapshot of the universe in motion. The cosmic microwave background plays a special role in the story of the Milky Way's fall toward the Great Attractor, and it is worth exploring that role in some detail. The cosmic microwave background, the afterglow of the Big Bang, fills all of space. It arrives at Earth from every direction, and if the universe were perfectly uniform and the Earth were at rest relative to it, it would arrive with exactly the same temperature in every direction. In practice, it is nearly but not quite perfectly uniform. There are tiny temperature fluctuations that encode the density variations of the early universe. But there is another, larger variation in the temperature of the microwave background that has a very specific form. When you move relative to the cosmic microwave background, the radiation ahead of you is slightly blue-shifted, appearing slightly hotter, and the radiation behind you is slightly red-shifted, appearing slightly cooler. This is the Doppler effect applied to the microwave background. The result is a dipole pattern, a variation in temperature across the sky that has one warm hemisphere and one cool hemisphere aligned with the direction of motion. Measurements of the microwave background dipole reveal that the local group of galaxies, including the Milky Way, is moving at roughly 630 kilometers per second relative to the background. This is the sum of all the peculiar velocities in the hierarchy: our orbital motion within the Milky Way's motion within the local group's motion within the Virgo Supercluster, and the overall flow of everything toward the Great Attractor and beyond. The direction of this motion is toward the constellation Centaurus, roughly in the direction of the Great Attractor. The alignment is not perfect because the total peculiar velocity includes contributions from many sources at different scales, but the dominant contribution at the largest scales is from the Great Attractor and the Shapley Supercluster, pulling the entire local group in that general direction. What makes this measurement particularly powerful is that the cosmic microwave background provides an absolute reference frame. It is not a motion relative to the nearest galaxy or the nearest cluster. It is a motion relative to the universe itself, relative to the average distribution of matter at the largest scales. When we say the Milky Way is moving at 630 kilometers per second towards Centaurus relative to the microwave background, we mean it is moving at that speed relative to the overall matter distribution of the universe. That is as close as we can get to an absolute velocity in the cosmological sense. The fact that the Milky Way has a significant velocity relative to the microwave background tells us directly that we are embedded in a large-scale gravitational flow. We are not simply riding the Hubble expansion. We are being accelerated by the concentrated mass of the structures around us. The microwave background dipole is the clearest and most direct evidence we have for the reality of the Great Attractor's pull. Something that sometimes surprises people when they first learn about the Great Attractor is that we are not the only things falling toward it. The Great Attractor is pulling at everything in a vast volume of space. It is not a special relationship between the Great Attractor and the Milky Way. It is a relationship between the Great Attractor and thousands of galaxies in the Laniakea Supercluster, all of them flowing toward the same general region. This means that the Milky Way is not alone in its fall. It is part of a convoy, a great migration of galaxies that are all being drawn toward the same gravitational center. The local group, the small cluster of galaxies that the Milky Way belongs to, is part of this migration. The Virgo cluster, the nearest rich cluster of galaxies, is part of it. The Centaurus cluster, closer to the Great Attractor, is part of it. Thousands of galaxies across a region spanning hundreds of millions of light-years are all participating in the same large-scale flow. This collective motion is one of the things that makes the Great Attractor such a significant cosmological feature. It is not just massive enough to pull at one galaxy or one group. It is massive enough to organize the motion of an entire supercluster. The basin of attraction that defines Laniakea is defined by the mass of the Great Attractor region, and everything within that basin is, in some sense, subject to its gravity. There is something almost social about this picture. The Milky Way is not making a solo journey. It is part of a vast community of galaxies, all headed in the same general direction, all sharing the same gravitational fate. The galaxies closer to the Great Attractor are further along in their fall, more affected by its pull. The galaxies farther away, like our own on the edge of the supercluster, are at the beginning of a journey they will never complete. But they are all part of the same flow. Thinking about the Milky Way as a member of this community can shift the way the fall feels in the imagination. It is less like a solitary plunge into darkness and more like a shared drift, a community of galaxies moving together through space under the influence of the same gravitational attraction. We are not alone in our falling. We are accompanied. One of the most interesting scientific questions raised by the Great Attractor and the Laniakea Supercluster is whether these structures are consistent with what the Standard Model of cosmology predicts. The Standard Model, based on cold dark matter and a cosmological constant representing dark energy, makes specific predictions about the distribution of matter and the growth of structure in the universe. It predicts, among other things, how massive superclusters should be, how large the flows toward massive concentrations should be, and how the peculiar velocity field should look in a universe like ours. The Great Attractor and Laniakea fall within the range of structures that the Standard Model can accommodate, though they are large and massive enough to be at the interesting end of the predicted distribution. More challenging for the model are questions about whether the flows measured toward the Great Attractor are consistent with the predicted amplitude of peculiar velocities in a cold, dark matter universe. Some measurements have suggested that the flows are larger than the Standard Model predicts. If the peculiar velocities of galaxies in our region are genuinely larger than the model expects, that would imply either that there is more mass concentrated in this region than the model accounts for, or that the model needs modification in some way. These discrepancies, if real, are at the level of statistical significance rather than dramatic contradiction. They are the kind of tension that drives refinement of models and motivates new observations rather than the kind of dramatic failure that requires a complete overhaul of the theoretical framework. But they are worth noting because they reflect the ongoing dialogue between observation and theory that characterizes the best science. The next generation of galaxy surveys, producing catalogues of tens of millions of galaxies with well-measured distances and velocities, will sharpen these tests considerably. If the flows are genuinely larger than the model predicts, those surveys will detect the discrepancy with much higher statistical confidence. If the flows are consistent with the model, that will provide strong support for our understanding of how large-scale structure forms. The Great Attractor, hidden for so long behind the zone of avoidance, has emerged as one of the most important test cases for cosmological theory. It is large enough, massive enough, and close enough to be studied in considerable detail, and what we learn from it will inform our understanding of the universe as a whole. There is something about the concept of falling that carries emotional weight beyond its physical meaning. In human experience, falling is usually associated with loss of control, with danger, with the sudden absence of the support that keeps us upright. We fall when the ground gives way, when we slip, when something unexpected removes the stability we had assumed was permanent. But the falling of the Milky Way toward the Great Attractor has none of these qualities. It is not a slip or a loss of balance. It is not the consequence of an unexpected removal of support. It is simply the response of matter to the existence of other matter. The fundamental behavior of mass in a gravitational field. It is as natural and as inexorable as the falling of water toward the sea. And in that naturalness, there is a kind of peace. The Milky Way is not falling because something went wrong. It is not in danger from the fall. The Great Attractor is not going to swallow our galaxy in any meaningful sense, at least not on any timescale that matters for the existence of life. The fall is simply the universe being the universe, matter participating in the gravitational dance that has been going on since the first structures formed in the early cosmos. When we say the Milky Way is falling into something, we mean it in the gentlest possible sense. A slow drift across hundreds of millions of light years, unfolding over billions of years, barely distinguishable from the general expansion of the universe, perceptible only through the most careful measurements. This is not catastrophe, it is choreography. The universe is always in motion, always falling somewhere, always drifting towards some concentration of mass or away from some void. The Milky Way is simply doing what everything does, participating in the gravitational structure of the cosmos, moving in response to the forces that shape the large-scale universe. And because those forces are enormous and those timescales are vast, the participation is invisible from our perspective. We feel none of it. We see none of it. We know it only because we have built instruments sensitive enough to detect it and mathematics subtle enough to interpret what those instruments tell us. That knowledge, that awareness of a motion we cannot feel, is one of the gifts of science. It expands the sense of where we are and what we are part of. It makes the universe feel larger, more dynamic, more alive, even as it reassures us that we are not in danger, that the falling is gentle, that we are being drawn through space by forces that have been at work since long before we existed and will continue long after we are gone. The Great Attractor has a hidden quality that goes beyond its location behind the zone of avoidance. It is also hidden in time. We see it not as it is now, but as it was when the light reaching our telescopes first left those distant regions of space. The light we receive from the Norma Cluster and the galaxies of the Great Attractor region has been traveling toward us for hundreds of millions of years. The galaxies we image when we point our telescopes at those coordinates are not showing us the present state of those galaxies. They are showing us how those galaxies looked when the universe was hundreds of millions of years younger than it is now. In that time, the Great Attractor region has continued to evolve. The galaxies within it have continued to merge and interact. The clusters have continued to accrete matter from the surrounding filaments. The gravitational field has continued to deepen. The Great Attractor of today, the region as it actually exists at this moment in cosmic time, is more massive, denser, and more structured than the one we observe. We are always seeing the past, and the Milky Way, falling toward the Great Attractor, is also seeing only its historical image. The gravitational pull we experience from the Great Attractor is not the pull of the Great Attractor as it is now. It is the pull as it was when the gravitational signal we are currently responding to was first emitted, in a sense. Gravity propagates at the speed of light, and the gravitational field we move in reflects the distribution of mass as it was some time ago. This temporal complexity is woven through all of cosmology. The universe we observe is always a reconstruction, built from signals that left their sources at many different times. The Milky Way navigates through a gravitational landscape that is always slightly out of date, always showing the universe as it was rather than as it is. And yet, the picture is coherent enough, the changes slow enough, that the historical image and the current reality are close enough for the motion to make sense. The Great Attractor was here before the light left it that we observe now. It will be here in some evolved form, when the light currently leaving it arrives at some distant observer millions of years from now. Our fall toward it is embedded in this larger temporal flow, one more process unfolding across timescales that dwarf any human frame of reference. By now, we have traveled through the discovery of the Great Attractor, its nature as a region rather than a point, the nesting of gravitational influences from the local group to Laniakea to the Shapley Supercluster, the role of dark energy in shaping the ultimate fate of the fall, and the profound temporal dimension of observing the distant universe. It is worth stepping back and thinking about what all of this means for our sense of where we are. For most of human history, the question of where we are had a simple answer. Here, in this place, on this patch of ground, in this village or city. The geography of the immediately surrounding world was the entirety of the known environment, and even as that geography expanded through exploration and cartography, it remained fundamentally local, bounded by the planet's surface. The expansion of the known universe over the past century has been one of the most dramatic shifts in the history of human self-understanding. From a local patch of ground to a planet, from a planet to a solar system, from a solar system to a galaxy, from a galaxy to a local group of galaxies, from a local group to a supercluster. Each step has pushed the horizon of the known world further outward, and each step has required a corresponding adjustment in our sense of what we are part of. The discovery that the Milky Way is part of Laniakea, a supercluster 520 million light-years across, is the latest of these expansions. It gives us a cosmic address that is dramatically larger than anything that came before. We are not just in the Milky Way. We are in the local group. We are in the outskirts of the Virgo Supercluster. We are in Laniakea, falling slowly toward the Great Attractor at its heart. That is a remarkable address. It places us in a specific location within the cosmic web, with a specific gravitational history and a specific gravitational future. It tells us not just where we are, but how we are moving, what we are connected to, what we are part of. The address is not just spatial, it is dynamical. It describes our place in the flow of the universe. Let's think for a moment about what future generations of astronomers might discover about the Great Attractor and the Milky Way's motion toward it. The surveys underway and planned for the next decade will be transformative. The Vera Rubin Observatory, with its ability to image billions of galaxies in the southern sky, will provide an unprecedented census of the galaxy population near and beyond the zone of avoidance. The Euclid mission will measure the shapes and redshifts of hundreds of millions of galaxies across a large fraction of the sky, enabling velocity field maps of far greater precision than anything available today. The Square Kilometre Array will detect neutral hydrogen across vast distances, probing the matter distribution in the regions most obscured by dust. With these new tools, the map of the peculiar velocity field, the map of how galaxies are moving through space, will become far more detailed. The contributions of different structures to the overall flow will be disentangled with greater precision. The mass distribution of the Great Attractor region will be constrained more tightly. The boundary of Laniakea, currently somewhat uncertain, will be defined more clearly. Perhaps most interesting is the prospect of mapping what lies even further behind the zone of avoidance. We know the Great Attractor is there, and we know roughly where it is and how massive it is. But the detailed structure of the galaxy population in that region remains poorly known compared to the rest of the sky. Future surveys using radio and infrared wavelengths will produce catalogues of galaxies in the zone of avoidance that approach the completeness of optical catalogues elsewhere in the sky. There is also the question of what lies beyond the Shapley Supercluster at even larger distances. If there are concentrations of mass beyond Shapley that are contributing to the overall peculiar velocity flow, future surveys with sufficient depth and sky coverage may detect them. The peculiar velocity field of the universe is a probe of the matter distribution at whatever scale you can measure it, and as our measurements extend to greater distances, they reveal structure at those scales. The story of the Milky Way's fall is not finished. It is an ongoing scientific narrative, with new chapters being written every year as surveys improve and methods advance. The ending of the story, such as it is, involves the long-term fate of everything under the influence of dark energy, a future so remote that it has no relevance to anything human. But the middle of the story, the exploration of what is pulling at our galaxy and how, is very much alive. Before we draw our thoughts together and allow this exploration to settle, there is one more thing worth sitting with. It is the question of what the Great Attractor represents in the largest possible context. We have described it as a concentration of mass, a region of enhanced galaxy density, the focal point of a supercluster. All of these descriptions are accurate, but in the context of the cosmic web, the Great Attractor represents something more general. It represents what happens when gravity is given enough time and enough matter to work with. The universe began in a state of extraordinary uniformity. The matter was almost perfectly evenly distributed. The deviations from perfect uniformity were tiny, perhaps 1 part in 100,000. But gravity is patient, and over 13.8 billion years, it has amplified those tiny deviations into the structures we see today. The filaments, the walls, the clusters, the superclusters. The Great Attractor is the product of gravity working on those initial fluctuations for the entire age of the universe. In this sense, the Great Attractor is not an anomaly. It is an outcome. It is what the universe produces when the initial conditions are what they were and gravity is what it is. The fact that it is so massive, so extended, so gravitationally dominant over such a large region of space is simply a reflection of the fact that the initial fluctuations in its direction were slightly larger than average and that gravity has had a long time to work. The same process that produced the Great Attractor produced all of the other large-scale structures in the universe. The Shapley Supercluster, the Perseus-Pisces Supercluster, the Coma Cluster, all of them are the products of gravity amplifying initial fluctuations over cosmic time. The Great Attractor is perhaps the most massive and most gravitationally dominant structure in our local patch of the observable universe. But it is not fundamentally different in kind from the other massive structures around it. What makes it special to us is its proximity and its influence. The Great Attractor is close enough and massive enough that its gravitational pull is detectable in the motion of thousands of nearby galaxies, including our own. It is the loudest gravitational voice in our cosmic neighborhood, and we are listening to it whether we know it or not. The night is quieter now. The images of the Great Attractor, the flow of thousands of galaxies across hundreds of millions of light years, the gentle, irresistible pull of concentrated mass on everything nearby, can begin to settle into the background of your awareness. The Milky Way is falling, right now, at this moment, 600 kilometers per second in the direction of Centaurus, toward the heart of the Laniakea Supercluster, toward the dense concentration of galaxy clusters that astronomers call the Great Attractor. You are on that journey. You have always been on that journey. Every living thing that has ever existed on this planet has been on that journey. And yet, nothing about daily life reflects this motion. The trees outside are not bending toward Centaurus. The rivers are not flowing in the direction of the Great Attractor. The morning will come, the birds will sing, the coffee will brew, and none of it will be any different for the knowledge that our galaxy is hurtling through space towards something vast and distant and partially hidden. That gap between the cosmic and the intimate is not a contradiction. It is simply scale. The motion is real and the life is real, and they occupy different levels of a universe that is large enough to contain both without conflict. The falling galaxy and the sleeping person are both part of the same story. The story is simply told at many different scales simultaneously, and each scale is complete in itself. To know about the Great Attractor is not to be overwhelmed by it. It is to be enlarged by it, to carry a piece of knowledge about where you are in the universe and where you are going, even if the going is too slow to feel and the destination is too far to see. That knowledge is a kind of compass, pointing in a direction that has nothing to do with north or south, but with the structure of the cosmos itself. The Milky Way is falling into something. That something is one of the largest concentrations of mass in the observable universe, the gravitational heart of the supercluster we call Laniakea, the immeasurable heaven. The fall is gentle and perpetual and shared by thousands of galaxies. It is the universe doing what it does, assembling itself, concentrating its matter, building its largest structures through the patient work of gravity across billions of years. And we are part of it. Small and temporary and completely unaware in our daily lives, but part of it nonetheless. Passengers on a galaxy that is falling through space towards something immense and beautiful and largely hidden at a speed we cannot feel, on a journey we will never complete. If you found something calming in following this drift through the cosmic scale, through the discovery of the Great Attractor and the mapping of Laniakea, and the gentle fall of everything toward the heart of our supercluster, you might find it worth returning to beyond the cosmos again. There is always another question at the edge of what we know. Always another current in the flow of the universe to follow. For now, let your breathing slow. Let the movement of the galaxy recede into the background where it lives, imperceptible and constant. You are here. The Great Attractor is there, hundreds of millions of light years away, patient and massive and pulling. And between you and it, stretching across the dark, is the falling universe, always in motion, always becoming what it is. Good night. There is a way of thinking about the Great Attractor that goes beyond the gravitational physics and the galaxy surveys and the peculiar velocity measurements. It is a way of thinking about what it means that the universe has objects like this at all. That the cosmos, beginning from near-perfect uniformity, could produce in 13.8 billion years a concentration of mass so extreme that it organizes the motion of everything within hundreds of millions of light years of it. The Great Attractor is not an accident. It is not a random fluctuation that happened to become enormous by chance. It is the predictable outcome of well-understood physics applied to specific initial conditions over a very long time. Given the initial fluctuation spectrum set by inflation in the very early universe, given the properties of dark matter and dark energy, given the laws of gravity and the rate of cosmic expansion, the formation of structures like the Great Attractor was not just possible, but inevitable. The cosmos was always going to produce them. The only question was where. In the language of physics, the Great Attractor represents what cosmologists call a high sigma peak. The density fluctuations in the early universe had a range of amplitudes. Most were small. Some were larger. A very few were the largest of all. The largest initial fluctuations grew over cosmic time into the largest structures. The Great Attractor, with its extraordinary mass and gravitational reach, grew from one of the largest initial fluctuations in our local patch of the universe. This is a beautiful and somewhat humbling thought. The fact that we live in the gravitational basin of such an extreme structure, that our galaxy is one of the thousands falling toward it, is a consequence of the particular initial conditions that prevailed in our corner of the universe 13.8 billion years ago. We did not choose this location. The Milky Way formed where the conditions allowed it to form, in a patch of space that happened to lie in the gravitational basin of one of the universe's largest concentrations of mass. We are, in this sense, the inheritors of a very specific cosmic history. And yet, that specificity is what gives us our place in the universe. Every detail of where we are and how we are moving reflects the particular history of our local patch of the cosmos. The Great Attractor is part of our history. The fall toward it is part of our situation. And knowing about it is part of knowing who we are. There is a related question worth exploring carefully, one that touches on the nature of the Great Attractor itself and on the limits of what we can currently observe. The question is whether the Shapley Supercluster is the final attractor, or whether there are structures even further away that are contributing to the overall flow. Some analyses of the peculiar velocity field have suggested that the flow toward the Shapley Supercluster does not fully account for all of the observed motion. There may be contributions from structures at even greater distances beyond the Shapley Supercluster that are pulling at the Milky Way and its neighbors. If so, the full picture of what the Milky Way is falling toward is even more complex than the one we have described. This possibility has a name in the literature. Some researchers have proposed the existence of what they call the dipole repeller, a structure in the opposite direction from the Great Attractor, a massive underdensity or void that is, in effect, pushing galaxies away from it and thereby contributing to the flow toward the Great Attractor. In 2017, a team led by Yehuda Hoffman mapped both attractors and repellers in the local universe and found evidence for a large void in the direction opposite to the Great Attractor that appeared to be pushing galaxies away, complementing the pull from Laniakea and Shapley. The dipole repeller adds another layer to the picture. The Milky Way is not just being pulled toward the Great Attractor. It may also be being pushed away from a large void in the opposite direction. The combination of being pulled from one side and pushed from the other creates a net motion that is consistent with the observed peculiar velocity of the local group relative to the cosmic microwave background. This push-pull dynamics is actually a natural feature of the way gravity works on the cosmic web. Voids push galaxies out. Superclusters pull galaxies in. The net flow of any given galaxy is the vector sum of all these influences. The Milky Way, sitting in the Laniakea Supercluster, is being pulled toward the dense heart of that supercluster while also being pushed away from the void regions that surround it. The two effects reinforce each other, both pointing in the same general direction of motion. Understanding the full balance of these forces, tracing all the attractors and repellers in our local universe, and quantifying their contributions is one of the active frontiers of large-scale structure research. Each new survey, each new catalogue of galaxy velocities adds information that allows the picture to be refined. We are still in the early stages of fully mapping the gravitational landscape that the Milky Way inhabits. The story of the Great Attractor is also a story about what science looks like when it is working at the frontier of the knowable. It is not a story of clean measurements and clear conclusions. It is a story of contested results, evolving interpretations, and gradually converging understanding. When the Seven Samurai published their 1988 paper proposing the Great Attractor, not everyone was convinced. Some astronomers questioned the distance measurements. Others argued that the flow they had detected was smaller than claimed or pointed in a slightly different direction. The zone of avoidance made it impossible to directly observe the putative source of the flow, which added to the uncertainty. Over the following years and decades, as more observations accumulated and methods improved, the debate slowly resolved. The Great Attractor became less controversial as more groups, using different methods and different galaxy samples, converged on consistent results. The opening of the zone of avoidance to infrared and radio surveys allowed the identification of the Norma Cluster and other massive structures at the expected location. The peculiar velocity measurements became more precise as the distance indicators improved. But new questions arose even as old ones were answered. When was Laniakea identified as the supercluster that the Great Attractor anchors? That was only 2014. Before that, the precise definition of our local supercluster was uncertain. Even now, the exact mass distribution of the Great Attractor region, the precise contribution of the Shapley Supercluster, and the role of structures beyond Shapley remain subjects of active investigation. This is what science at the frontier looks like. Not a march from ignorance to complete knowledge, but a gradual refinement of understanding, with each generation of measurements and analyses giving a slightly clearer picture, while also revealing new layers of complexity that were hidden at the previous level of resolution. The Great Attractor has been known for nearly 4 decades, and we are still learning new things about it. This process of gradual refinement is not a failure. It is the nature of scientific progress when the object of study is genuinely complex and genuinely challenging to observe. The Great Attractor is hidden, vast, and comprehensible only through indirect measurements. That it has been understood as well as it has in just a few decades of intensive study is a remarkable achievement. Among the things that make the Great Attractor scientifically valuable is what it can tell us about dark matter. The mass required to explain the observed peculiar velocity flows is far greater than the mass visible in the galaxies and gas of the Great Attractor region. As with galaxy clusters and the galaxy rotation curves that first suggested dark matter's existence, the dynamics of large-scale flows, like the one toward the Great Attractor, require a dark component of matter that outweighs ordinary matter by a substantial factor. In the Great Attractor region and in the Laniakea Supercluster more generally, dark matter is thought to constitute roughly 85% of the total mass. The galaxies and hot gas we can observe in X-rays and optical light are the minority, the visible tip of an enormous dark iceberg. The gravitational pull that is drawing the Milky Way and thousands of other galaxies toward the Great Attractor is primarily the pull of this invisible dark matter. This means that when we talk about falling toward the Great Attractor, we are falling primarily toward a concentration of something we cannot see. The galaxies of the Norma Cluster, spectacular as they are in infrared images, are not the primary gravitational actors. They are embedded in a dark matter halo that extends far beyond the visible galaxy distribution, that contains most of the mass, and that is responsible for most of the gravitational influence. Dark matter does not interact with light. It cannot be directly imaged, but it can be mapped through its gravitational effects. The peculiar velocity measurements that identified the Great Attractor are, in a very real sense, a dark matter map. They reveal the distribution of total mass, visible and invisible, by tracing how that mass affects the motion of everything around it. The flow of galaxies toward the Great Attractor is a signature of dark matter as much as it is a signature of the visible galaxy concentration. This makes the study of large-scale flows like the Laniakea Basin particularly important for understanding dark matter. On the scale of individual galaxies, dark matter reveals itself through rotation curves and gravitational lensing. On the scale of clusters, through the dynamics of member galaxies and the temperature of hot X-ray emitting gas. On the scale of superclusters and cosmic flows, through the systematic peculiar velocities of thousands of galaxies. Each scale provides a different probe of the same invisible substance, and the consistency of the results across all scales is one of the strongest arguments for dark matter's reality. There is something about the scale of the Great Attractor and the flow it generates that puts our own place in the universe into a particular kind of relief. We have spoken about the Milky Way as one of thousands of galaxies falling toward the Great Attractor. But it is worth being specific about where in that flow we are. The Milky Way is not near the center of Laniakea. It is on the edge, near the periphery of the supercluster. The Great Attractor region, the dense heart of Laniakea, is hundreds of millions of light-years away. We are not in the thick of the gravitational action. We are in the outer reaches, the suburban rim of a vast cosmic structure. This location on the periphery has its advantages. Galaxies near the centers of massive clusters and superclusters exist in a turbulent gravitational environment. They interact frequently with other galaxies. The hot gas that fills the intracluster medium can strip gas from infalling galaxies, suppressing star formation. The dense gravitational environment accelerates evolution in ways that can be both productive and destructive. On the edge of Laniakea, the Milky Way has been able to evolve in a relatively calm environment. The interactions with other galaxies have been less frequent, less violent. The gas reservoir that fuels star formation has been less depleted by environmental effects. The calm periphery of the supercluster may be one of the reasons our galaxy has the properties it does, including the relatively steady rate of star formation that produced, over billions of years, a sun and a solar system and a planet capable of supporting life. The Great Attractor has been pulling at us for as long as the Milky Way has existed, but from far enough away that its influence has been a gentle nudge rather than a violent disruption. We are close enough to be affected, distant enough to be spared the most disruptive effects. Our position in the gravitational landscape of Laniakea is, from the perspective of life on Earth, a fortunate one. This is not to say that position was chosen, or that life requires it. Life might be possible in galaxies much closer to the centers of rich superclusters. But it is interesting to note that the cosmic address that the Milky Way occupies, on the quiet edge of a vast supercluster falling slowly toward a distant attractor, is the address at which a habitable planet formed and life emerged. Our specific place in the gravitational architecture of the universe is part of the context within which we exist. The history of ideas about the large-scale structure of the universe is worth reflecting on, because it shows how dramatically our picture of the cosmos has changed in a relatively short time. A century ago, the universe, as understood by astronomers, was essentially the Milky Way. Other galaxies were not yet known to be separate systems. The idea of a cosmic web, of superclusters and voids and large-scale flows was entirely beyond the conceptual horizon. The universe was a single galaxy of stars, and the questions about it were primarily about the stars and gas within that galaxy. Then came Hubble's measurement of galaxy distances in the 1920s, and suddenly the universe expanded by an enormous factor. It was not one galaxy, but millions, each a Milky Way of its own, scattered across space to distances that dwarfed the scale of the galaxy itself. The universe became much larger, much emptier, and much more complex. Through the middle of the 20th century, galaxies were studied and catalogued, and the first hints of clustering, of galaxies preferring to be near other galaxies, began to emerge. The Virgo cluster, the Coma cluster, and other concentrations of galaxies were identified and studied. But the idea of the cosmic web, of the organized large-scale structure of the universe, was not yet clear. It was the redshift surveys of the 1970s and 1980s that revealed the web. The Great Wall, the first great sheet of galaxies to be mapped, the Boötes Void, the Great Attractor, all emerged from these surveys as evidence that the universe has structure on scales far larger than individual clusters. The cosmos was not just galaxies scattered through space. It was a web, with galaxies concentrated in filaments and walls and nodes and enormous voids between them. And then came the precision era, the large surveys like the Sloan Digital Sky Survey that mapped hundreds of millions of galaxies and produced three-dimensional maps of the universe of unprecedented detail. These surveys confirmed and extended the picture from the 1980s, revealing the cosmic web in all its complexity and enabling the statistical tests of cosmological models that drive the field today. The Great Attractor sits within this history as one of the pivotal discoveries. It was found at a moment when the picture of large-scale structure was still being assembled, when the existence of structures on the scale of superclusters was just beginning to be understood. Its discovery helped motivate the surveys and the theoretical work that have since produced our current picture of the universe. It is not just a feature of the cosmos. It is a chapter in the history of human understanding of the cosmos. As we approach the end of this long exploration, let's take a moment to think about what it means to live in a galaxy that is part of a supercluster, falling toward a great concentration of mass, moving through space at hundreds of kilometers per second in a direction defined by the structure of the universe on its largest scales. One response to this knowledge is awe. The sheer scale of what we are part of, the Milky Way as one of thousands of galaxies in a supercluster 520 million light-years across, that supercluster itself embedded in a larger cosmic web, all of it moving and falling and flowing according to the laws of gravity and the properties of dark matter and dark energy, is genuinely magnificent. It is the universe demonstrating its capacity for complexity and structure at every scale, from the atoms in your body to the superclusters that organize the motion of entire galaxies. Another response is perspective. The concerns of daily life, the anxieties and frustrations and minor dramas that occupy most of our attention exist at a scale so far removed from the scale of the Great Attractor that they seem, if not unimportant, then at least proportionate. We are small, our time here is brief, but we are also part of something vast and coherent and magnificent. The same physics that organized the Great Attractor, that drew together hundreds of thousands of galaxy masses into a concentrated region of space, is also at work in every falling leaf, every rising tide, every heartbeat. Gravity connects the Milky Way's fall toward the Great Attractor to the apple falling from the tree. The scale is different, but the mathematics is the same. A third response is curiosity. The story of the Great Attractor is not finished. There is still so much to learn about what it is, how it formed, what lies beyond it, and how the flow of galaxies toward it fits into the larger picture of cosmic structure. The next generation of surveys will answer some of these questions and raise new ones. The universe always has more to reveal, and perhaps the most appropriate response is simply presence. To know that the Milky Way is falling into something, to have spent time understanding what that something is and why the fall is happening, and then to let that knowledge settle quietly into the background of awareness. Not something to worry about, not something to do anything about, simply something to know. A fact about the universe and about our place in it, carried lightly, held with curiosity, allowed to deepen the sense of what we are part of. The Great Attractor will be there tomorrow and the day after, and for billions of years to come. The Milky Way will continue its fall, together with its thousands of companion galaxies in Laniakea, drawn by the concentrated mass of a region of the universe that remained hidden for most of the history of astronomy. The fall is gentle and perpetual and indifferent to whether anyone notices it. But we have noticed it. Scientists working with spectrographs and distance indicators and statistical methods have teased out the signal of this enormous motion from the noise of individual galaxy measurements. They have mapped the flow, defined the supercluster, named the attractor. They have given us, for the first time, a clear sense of our place not just in the galaxy or the local group, but in the vast gravitational structure that organizes the motion of everything in our cosmic neighborhood. That is a remarkable gift. To live in a time when the instruments and the methods and the accumulated knowledge exist to detect something as subtle and as vast as the fall of the Milky Way toward the Great Attractor. To live in a culture where such knowledge is sought and valued and shared. To have access, in the quiet of an evening, to a story that places your own small life in the context of the largest structures in the observable universe. You are on a planet, orbiting a star, inside a galaxy that is falling through space at hundreds of kilometers per second toward a massive concentration of matter hundreds of millions of light years away. You are part of the largest gravitational flow in our local patch of the cosmos. You are a passenger in the Laniakea Supercluster, sharing the journey with thousands of other galaxies, all drawn by the same invisible hand toward the same distant destination. And all of that is happening while you breathe, while your heart beats, while the ordinary details of a human life unfold around you. The cosmic and the intimate coexist, layered on top of each other, each real and complete in its own scale. If you found something in this exploration that felt enlarging, something that shifted the sense of what you are part of or where you are, then Beyond the Cosmos has done what it set out to do. There is always another question at the horizon, another current in the cosmic flow to trace. Come back when you need the perspective that comes from thinking about things vastly larger than the everyday. For now, let the Great Attractor recede to its proper place, hundreds of millions of light years away, patient and massive, pulling at everything nearby with the quiet authority of concentrated mass. And let the Milky Way continue its fall, as it has been falling for billions of years, gently and steadily towards something immense and beautiful and waiting. There is one more layer to the story of the Great Attractor that we have not yet fully explored. It concerns the relationship between the Great Attractor and the observable universe as a whole, and what the existence of such a massive structure tells us about the statistical properties of the cosmos. The universe, at its largest scales, is expected to be statistically homogeneous and isotropic. That is, on average, the universe looks the same in every direction and from every location. This is called the cosmological principle, and it is one of the foundational assumptions of modern cosmology. The cosmic microwave background, the distribution of galaxies on large scales, the overall rate of expansion, all of these are consistent with this principle. But the cosmological principle applies on average, on the very largest scales. On smaller scales, like the hundreds of millions of light years that define the Laniakea Supercluster, the universe is very much not uniform. There are concentrations of mass and regions of emptiness, attractors and repellers, filaments and voids. The Great Attractor is a concrete example of how non-uniform the universe can be on these smaller but still enormous scales. The existence of the Great Attractor is consistent with the cosmological principle because the principle says nothing about what happens on the scale of superclusters. It says only that if you average over scales of billions of light years, the universe looks the same everywhere. On those scales, the Great Attractor is just a small perturbation. The Laniakea Supercluster, vast as it is tiny compared to the observable universe's 93 billion light-year diameter. Nevertheless, the Great Attractor is at the large end of the structures that the standard cosmological model predicts. The model, based on cold dark matter and dark energy, makes predictions about the statistical distribution of structures of all sizes, from the smallest dwarf galaxies to the largest superclusters. The Great Attractor, with its mass and its gravitational reach, tests those predictions at the extreme end. As measurements of its mass and the flow it generates become more precise, they will provide increasingly stringent tests of the model. This is why structures like the Great Attractor are scientifically important beyond their intrinsic interest. They are test cases for our fundamental understanding of how the universe works. If the model correctly predicts the existence of structures as massive and as influential as the Great Attractor, that is strong evidence that the model is on the right track. If future, more precise measurements reveal that the Great Attractor is more extreme than the model comfortably accommodates, that tension will point toward new physics, toward modifications of the model or additions to it. The Milky Way's fall toward the Great Attractor is therefore not just a fact about our cosmic situation. It is a measurement. The amplitude of our peculiar velocity, the direction of our motion, the extent of the flow that carries us and thousands of our neighbor galaxies toward the same destination, all of these are data points for the theory of how the universe grows its largest structures. We are both the observers and the observed. The concept of the dipole, which we touched on earlier in the context of the cosmic microwave background, deserves a bit more attention because it is one of the most elegant tools astronomers have for studying the large-scale motion of our galaxy. A dipole is a pattern with two poles, one positive and one negative. When you stand on a moving train and listen to a whistle outside, the pitch of the whistle is higher in the direction you are moving toward and lower in the direction you are moving away from. This is the Doppler effect, and it creates a dipole pattern in the distribution of pitch around you. The cosmic microwave background dipole works on the same principle. The entire sky of microwave background radiation appears very slightly warmer in the direction we are moving toward and very slightly cooler in the direction we are moving away from. By precisely measuring the temperature of the microwave background across the whole sky, astronomers can detect this dipole and extract from it the speed and direction of the local group's motion relative to the overall matter distribution of the universe. The result, as we mentioned, is a motion of about 630 kilometers per second toward the constellation Centaurus. This is a precise and well-measured number. It is the sum of several contributions: the Earth's orbit around the Sun, the Sun's orbit around the Milky Way, the Milky Way's motion within the local group, and the local group's motion toward the Great Attractor and beyond toward Shapley. Each of these contributions can be estimated from other measurements, and when they are subtracted from the total, what remains is the cosmological peculiar velocity, the motion of the local group relative to the cosmic rest frame. This motion is what the Great Attractor and the other large-scale structures in our neighborhood are responsible for. The dipole is also useful as a check on other measurements. If the peculiar velocities measured from galaxy surveys are consistent with the amplitude and direction of the microwave background dipole, that provides confidence that both measurements are correct. Inconsistencies between the two would signal problems with either the galaxy surveys, the microwave background analysis, or both. In practice, the measurements have been broadly consistent, with some remaining tensions at the level of detail that active research is working to resolve. The microwave background dipole and the galaxy peculiar velocity surveys are two independent probes of the same large-scale motion, and their agreement is one of the pieces of evidence that the Great Attractor and its associated flow are real features of the universe. There is a dimension to the falling of the Milky Way that connects, in an unexpected way, to the question of the universe's ultimate fate. We have discussed how dark energy, the accelerating expansion of space, is likely to prevent the Milky Way from ever reaching the Great Attractor. Over the very long term, dark energy will stretch the distances between all galaxy groups and clusters that are not gravitationally bound to each other. The Milky Way and Andromeda will eventually merge, drawn together by their local gravity. The local group will remain bound. But the great flow toward the Great Attractor, the organized drift of thousands of galaxies across hundreds of millions of light years, will eventually be disrupted. This disruption will happen not all at once, but gradually. The galaxies farthest from the Great Attractor, on the outermost edges of the Laniakea Supercluster, will be the first to have their fall arrested and reversed by the expansion. Galaxies closer to the Great Attractor will remain in the flow longer, their local gravity stronger relative to the dark energy pressure. Eventually, over billions to trillions of years, the supercluster will dissolve, leaving behind only the gravitationally bound knots, the clusters and groups, as isolated islands in an expanding void. The Milky Way, merged by then with Andromeda into a larger elliptical galaxy, will be one of those islands. The Great Attractor, or what remains of it after its own evolution over those timescales, will be another. Both will persist as gravitationally bound structures, but the flow connecting them will be gone. The current fall of the Milky Way towards the Great Attractor is a feature of the universe's middle age, when structure formation is still active and large-scale flows are still organizing the cosmic web. In the universe's old age, these flows will cease and the cosmic web will freeze and then dissolve. In the very far future, the universe will be a collection of isolated gravitationally bound structures surrounded by expanding voids with no large-scale flows connecting them. The cosmic web will be gone. The supercluster boundaries will mean nothing. The Great Attractor will pull at nothing beyond its own cluster members. But that is so far in the future as to be almost conceptually inaccessible. In the present, the flow is real, the fall is ongoing, and the universe is still in the productive middle period of its history when structure formation is actively shaping the cosmic web. We are fortunate, in a sense, to live at this particular moment when the universe is rich enough to have produced us and structured enough for the Great Attractor to be doing its work. Let's think for a moment about the human beings who have dedicated their careers to understanding the Great Attractor and the large-scale motions of galaxies. Because the science we have been exploring does not happen by itself. It is made possible by specific people, asking specific questions, developing specific methods, spending years or decades on problems that do not yield to quick approaches. The Seven Samurai, the informal name for the group of astronomers who first identified and named the Great Attractor in the 1980s, spent years measuring the distances to hundreds of elliptical galaxies using the fundamental plane relation. This is painstaking work. Each galaxy requires telescope time, careful spectroscopic measurements, precise photometry, and careful error analysis. The scatter in the fundamental plane relation means that each individual galaxy distance is uncertain at the level of 20% or so. To detect a peculiar velocity flow at the level of a few hundred kilometers per second against a Hubble velocity of thousands of kilometers per second requires measuring hundreds of galaxies and averaging over the scatter. Brent Tully and his collaborators, who have been measuring galaxy distances and peculiar velocities for decades, have assembled catalogues of thousands of galaxies with carefully measured distances. The Cosmic Flows project, which produced the velocity maps used to define Laniakea, represents an enormous investment of telescope time, data reduction effort, and intellectual work. The result, the map of the velocity field that revealed the supercluster structure, is one of the most detailed pictures of large-scale cosmic motion ever produced. Behind every data point in those catalogues is a night at a telescope, a spectrum carefully reduced, a distance carefully estimated, an error carefully propagated. The Great Attractor is known as well as it is because people put in that work, systematically and patiently, over decades. This is worth remembering because it is easy to present scientific results as if they appeared fully formed, as if the Great Attractor declared itself to astronomers who simply looked in the right direction. The reality is far more laborious and far more human. The discovery of the Great Attractor and the mapping of Laniakea are achievements of sustained scientific effort carried out by researchers who cared deeply about understanding where we are and how we are moving. Their work has given us a picture of our cosmic situation that is both humbling and magnificent. We know something real and precise about the large-scale motion of our galaxy. We know the direction we are falling, roughly how fast, and toward what. We know the boundaries of the supercluster we belong to and the gravitational structure that defines those boundaries. That knowledge is a gift from the scientists who built the instruments, wrote the code, reduced the data, and interpreted the results. As we near the end of this exploration, it is worth asking a simple question one more time and trying to give it the most complete and honest answer we can. What is the Milky Way falling into? It is falling into the Great Attractor, which is the gravitational focal point of the Laniakea Supercluster. The Great Attractor is not a single object but a region centered roughly on the Norma Cluster and its surrounding galaxy concentration spanning tens of millions of light-years, containing a mass of hundreds of thousands of times the Milky Way's mass and situated behind the dust-obscured plane of our own galaxy in the constellation Norma. But the Great Attractor is itself part of something larger, and the fall of the Milky Way is part of a larger flow. The Great Attractor and Laniakea are themselves being pulled toward the Shapley Supercluster, 650 million light-years away, one of the most massive concentrations of matter in the observable universe. And possibly, contributions from structures even further away are also part of the picture. At the same time, the Milky Way is being pushed away from a large void in the opposite direction, the dipole repeller, whose relative emptiness creates a gravitational imbalance that reinforces the flow toward the Great Attractor. The net motion of the Milky Way is the result of all these influences together, attractors pulling and repellers pushing, all adding up to a velocity of about 630 kilometers per second, relative to the cosmic microwave background directed toward the Centaurus constellation. This is where we are going. Not by choice, not by intent, but by gravity, which is to say, by the fundamental nature of matter in a universe that began in near-perfect uniformity and has been differentiating ever since. The Milky Way is falling into the result of 13.8 billion years of gravitational amplification of tiny initial fluctuations. It is falling into the cosmic web's most prominent local feature. It is falling into structure, into concentration, into the accumulated consequence of the universe doing what it does. And the fall will continue, gentle and imperceptible and vast, for as long as the universe allows it. There is a final image that seems right for the end of this exploration. Not a dramatic image, not something bright or explosive or violent, something quiet, in keeping with the nature of the fall itself. Imagine a night sky with no light pollution. You are somewhere remote, the air cool and still, the stars overhead in their full abundance. The Milky Way stretches from horizon to horizon, a river of light, a suggestion of the galaxy's disk seen from inside. The constellations are arranged as they always are, the familiar patterns that humans have been naming since before written history began. Somewhere in the southern sky, if you are in the right hemisphere, the small and faint constellation Norma is present. It is not much to look at. A few dim stars, no particular pattern that catches the eye, easily overlooked. But behind those stars, behind the dust and gas of the Milky Way's plane, hundreds of millions of light-years in the background, the Great Attractor is there. The Norma Cluster and its associated galaxy concentration, vast and dark and massive, doing what it has always done, pulling everything within its reach toward its dense heart. And the ground beneath your feet, and the atmosphere around you, and the planet supporting you, and the sun 150 million kilometers away, and the Milky Way enclosing all of that, is moving. Right now, toward that barely visible point in the sky, at 600 kilometers per second, silently, invisibly, continuously, alongside thousands of other galaxies, all sharing the same gravitational fate, all part of the same supercluster, all falling toward the same attractor. You cannot feel it. The night is still. The stars do not seem to move. The world around you is calm, and yet the motion is real as anything in the universe, as fundamental as gravity itself, as old as the galaxy. To stand under that sky and know this, even for a moment, is to feel both very small and very connected. Very small, because you are one person on one planet in one galaxy among thousands. Very connected, because the motion you are part of links you to all of those thousands of galaxies, to the concentrated mass of the Great Attractor, to the structure of the Laniakea Supercluster, to the cosmic web, to the initial conditions of the Big Bang from which all of this arose. You are falling. Everything is falling. And the falling is beautiful. If the quiet scale of this journey through the cosmos has been a companion tonight, you are welcome to return to Beyond the Cosmos whenever you need the perspective that comes from thinking about things vastly larger than the immediate. There is always something more to explore, always another current in the cosmic flow to follow, always another way the universe reveals its structure and its depth. For now, let the fall recede into the background where it belongs. Constant, gentle, vast. Let your breathing slow. Let the Great Attractor pull at the galaxy without asking anything of you tonight. The Norma Cluster itself deserves a moment of focused attention because it is the most massive identifiable galaxy cluster at the heart of the Great Attractor region, and it has properties that are remarkable even by the standards of galaxy clusters. The Norma Cluster, designated Able 3627, was first identified as a cluster of galaxies in the 1950s, but its true nature as one of the most massive clusters in the nearby universe was not appreciated for decades because of its location behind the zone of avoidance. Early optical surveys could not penetrate the dust of the Milky Way's plane, and the cluster was visible only as a partial, obscured collection of galaxies rather than the magnificent structure it actually is. When infrared and radio surveys began revealing its true extent in the 1990s, the picture that emerged was of a cluster comparable in richness to the Coma Cluster, one of the most studied and best-known galaxy clusters in the sky. The Norma Cluster contains thousands of galaxies, bound in a roughly spherical volume perhaps 10 to 15 million light-years across, filled with hot X-ray emitting gas that records in its temperature the depth of the gravitational potential, the cluster creates. The X-ray emission from the Norma Cluster, detected by X-ray satellites that can see through the obscuring dust of the Milky Way, reveals a hot gas halo at tens of millions of degrees, heated by the gravitational compression of infalling material. This X-ray glow is a diagnostic of the cluster's mass and dynamical state. The temperature of the gas reflects the depth of the potential well, and the depth of the potential well reflects the total mass, including dark matter. The Norma Cluster is also notable for being somewhat disturbed dynamically, not a perfectly relaxed spherical system, but one that shows signs of ongoing accretion and possible merging with subclusters. This suggests that the cluster is still actively growing, still incorporating material from the surrounding environment, still evolving toward whatever its final, fully relaxed state will be. In this sense, The Great Attractor's heart is not a finished product, but a work in progress, a massive structure that is still assembling itself even now. The ongoing accretion of matter onto the Norma Cluster is itself a manifestation of the same process that draws the Milky Way toward the Great Attractor. The flow of galaxies toward the cluster center and the flow of hot gas along filaments into the cluster are the local scale version of the same gravitational dynamics that produce the large-scale peculiar velocity flow. At every scale, the physics is the same. Matter flows toward concentrations of mass, and concentrations of mass grow by accreting that matter. The Great Attractor is the local universe's most dramatic example of this universal process. The story of the Great Attractor is ultimately a story about gravity, about what gravity does when given enough matter and enough time, about how a force that is by far the weakest of the fundamental forces at the particle level becomes, on cosmic scales, the dominant organizer of structure, about how the same mathematics that describes the fall of an apple from a tree also describes the fall of the Milky Way toward a concentration of matter hundreds of millions of light years away. Isaac Newton worked out the basic mathematics of gravity in the 17th century, motivated by questions about the motion of the moon and the planets. He could not have imagined that the same inverse square law he derived would, 3.5 centuries later, be used to understand the motion of entire galaxies across hundreds of millions of light years. And yet, it does. The physics of gravity is scale-free in this sense. The same equations work from the scale of a falling stone to the scale of a falling galaxy, modified only by the geometry of space-time that Einstein's general relativity provides for the very largest scales. The fall of the Milky Way toward the Great Attractor is, in this sense, a vindication of Newton and Einstein both. Newton's gravity provides the basic framework for understanding why matter flows toward concentrations of mass. Einstein's general relativity provides the more complete framework needed to understand the expanding universe, the cosmic microwave background, and the propagation of gravitational influences at the speed of light. Together, they give us the tools to measure and interpret the motion of our galaxy through the universe. And the motion is not just a curiosity, it is a probe. The peculiar velocity of the Milky Way and of all the galaxies in the Laniakea Basin is a measurement of the gravitational field produced by all the matter in the surrounding universe. By measuring how we are moving, we learn about what is out there. We learn about the distribution of dark matter. We learn about the structure of the cosmic web. We learn about the balance between gravity and dark energy that determines which structures survive and which dissolve. Every time an astronomer measures the peculiar velocity of a distant galaxy, they are contributing to this picture. Every redshift survey, every catalogue of galaxy distances, every careful map of the velocity field adds information that refines our understanding of where the mass is and how it is organized. The fall of the Milky Way toward the Great Attractor is, in a very real sense, one of the most informative facts about the large-scale structure of the universe. And we are the fact. As we prepare to let this long exploration settle into rest, there is one thought worth holding gently as you drift towards sleep. The Great Attractor is not trying to pull you anywhere. It is not aware of you. It is not aware of the Milky Way. It is simply a concentration of matter doing what concentrations of matter do, attracting everything around them through the universal language of gravity. There is no drama in it, no intent, no destination being reached or avoided. Only the patient, continuous application of a force that has been operating since the first structures formed in the early universe. And yet, the effect of that patient force is what you are part of. The flow of the Milky Way toward the Great Attractor, gentle and vast and billions of years old, is your cosmic inheritance. It is the gravitational context into which the solar system was born and within which every human life has been lived. It is, in the deepest sense, home. Home is not always where you are. Sometimes it is what you are moving through. The Milky Way is falling, and in that falling, it is home to every star and planet and moon in its 100 billion star family. It is home to the blue marble of Earth. It is home to the thin layer of air and water and soil that makes life possible. It is home to every living thing that has ever drawn breath or turned toward the sun. And all of it, together, is moving towards something vast and distant, pulled by a force no one can feel, at a speed no one can detect, on a journey no one will live to complete. The falling is permanent. The home is constant. The motion is the stillness. That is the Great Attractor's gift to the imagination. Not a threat, not a destination, but a reminder that the universe is always in motion and that we are always part of that motion. The ground is not still. The galaxy is not still. The supercluster is not still. Everything is falling. Everything is flowing. Everything is participating in the gravitational ballet that turns initial uniformity into the extraordinary structure of the cosmos. And in the midst of all that motion, here you are, still, breathing, resting, part of a falling galaxy and completely at peace with that fact. Before we truly rest, there is one final dimension worth bringing into the light. It concerns not just what the Milky Way is falling toward, but what that falling tells us about the nature of our knowledge itself. We have, over the course of this exploration, described the Great Attractor with considerable confidence. We have named its location, estimated its mass, mapped the flow of galaxies toward it, and described its relationship to the Laniakea Supercluster and the Shapley Supercluster beyond. But it is worth being honest about how this knowledge was assembled and about the limits that still remain. The zone of avoidance still partially obscures the Great Attractor region. While infrared and radio observations have revealed much of what lies there, the optical completeness of the galaxy catalogue in that part of the sky is still lower than elsewhere. There may be galaxy concentrations in the Great Attractor region that have not yet been catalogued. The total mass of the region may be larger or differently distributed than current estimates suggest. The peculiar velocity measurements that originally identified the Great Attractor flow and that continue to define our best picture of it are statistical. Individual galaxy distances have uncertainties of 15 to 25%. The flow signal is extracted by averaging over hundreds or thousands of galaxies, and the systematic errors in the distance indicators can propagate into systematic errors in the peculiar velocity maps. Different research groups using different methods and different galaxy samples sometimes arrive at somewhat different pictures of the velocity field. And the question of what lies beyond Shapley, whether there are concentrations of mass at even greater distances that contribute to the flow, remains genuinely open. The peculiar velocity field at very large distances is poorly measured, and what is there in the far background may be influencing the motion of everything nearby in ways that are not yet fully captured by the current data. None of this means that the picture we have described is wrong. It means that it is the best available picture, assembled from the best available data, and that future observations and analyses will refine it. Science does not work by producing perfect answers. It works by producing progressively better approximations to the truth, each one more precise and more reliable than the last, each one revealing new aspects of the phenomenon being studied. The Great Attractor, discovered by feeling its gravitational pull before its source was seen, understood progressively over 4 decades of improving observations, connected to the larger structure of Laniakea in 2014, and still being refined today, is a beautiful example of how science works when the object of study is genuinely difficult. It rewards patience. It rewards precision. It rewards the willingness to sit with uncertainty while accumulating the evidence that gradually reduces it. We know more about the Great Attractor now than we did in 1988. We will know more about it in 2035 than we do today. The story is ongoing. The knowledge is incomplete. And that incompleteness is not a reason for doubt, but a reason for continued curiosity. The Milky Way is falling. You are on the Milky Way. The fall is real, continuous, ancient, and gentle. The destination is the heart of the Laniakea Supercluster, the Great Attractor, hundreds of millions of light-years away, pulling at everything in its basin with the quiet authority of concentrated mass. The journey will not be completed in any human lifetime, or in the lifetime of our species, or perhaps ever if dark energy has its way. And none of that matters for tonight. Tonight, the fall is happening in the background, as it always has, as it always will. The galaxy moves, the stars shine, the planet turns, and here, on the surface of a small world orbiting one of those stars, you are resting, warm, comfortable, safe, in a universe that is vast and structured and moving and alive. The Great Attractor pulls at the Milky Way. The Milky Way holds the solar system. The solar system holds the Earth. The Earth holds you. And you hold, in whatever way the mind holds things, the knowledge of what is out there and what it is doing. That knowledge is small compared to the scale of what it describes. But it is real, and tonight it is yours. Beyond the Cosmos will be here when you want to explore again. The universe is patient, the questions are always waiting, and the next question, whatever it is, will be as large and as quiet and as worth sitting with as this one has been. For now, simply rest. The fall continues. The galaxy moves. The Great Attractor waits. Good night.